So my name is Liu Zhi, and you can also call me Martin. So I'm a PM at the RisingWave Labs. I used to do also like a database kernel development. So I would say that actually Boyan's talk makes my job much easier because he has already covered many streaming-related concepts, and especially he discussed some of the complexities and issues, problems they were facing when using a specific streaming system to do multi-streaming join, which is real-time data enrichment in this case. I would say my job today is here actually to convince you that the issues they were facing is not about the stream processing technology in general, but actually it is tied to the failure of a specific system. Right? So with RisingWave's help, I assume that most of the users will not face such difficulties in the future. Okay, so RisingWave. So RisingWave is a streaming database, right? So the first question is like, what's streaming processing? So stream processing and OLAP, they are not like a one to replace the other relationship. It's more like each of the processing paradigm tries to solve a different use case. Right? So when people first came up with stream processing, they asked the question like, in real world, the data is generated continuously. So why do we process these data continuously so that we can acquire insights continuously and with low latency, right? So the idea is that you're facing an infinite stream of data where you have a fixed query. So whenever there are new data coming to the system, the query react to the data. For the OLAP system, it's more like you have a finite set of data, right? So and the data analyst, business analyst, they will try to explore what's contained in that data set. So they will come up with different queries, right? Get those insights, and based on the insights, they modify the queries and try to get more different insights. The idea is basically the data set is fixed, but the queries are changing, right? This is the first difference between stream processing and OLAP. So the key benefits of stream processing is really about incremental computation, right? So the idea is very straightforward. Let's say you have 1 billion values you want to sum up, right? So you do the summation, you get one final sum, and then it comes another new value. You ask the question like, what's the new sum of these 1 billion plus one value, right? So any reasonable person would say, why don't we just use the previously generated result and plus this new value and have the new result, right? So this is basically the essence of incremental computation. But of course, in RisingWave, we are not really just doing like summation. We can also do all kinds of aggregation, all types of joins you can find in a traditional database, and all these window over function, just like when you're using for example, Doris, right? And for OLAP, you have to like scan over the data set every time when you execute a query. This is also why Wade and Boyan talks about materialized view, right? They want to kind of pre-compute the query result, and then they can use it over and over again to reduce the cost. But the thing here is that the materialized view is actually static, right? So if there are new data coming into the system, you have to manually refresh the data to get a new materialized view. So there is a kind of an intrinsic trade-off between the freshness and also the computation cost. And with RisingWave, you don't need to make this trade-off anymore because you have incremental computation. So the materialized view in RisingWave is incrementally computed, updated, right? So every time when you do some incremental computation, the amount of computation it triggers is only related to the size of the new data, right? It has nothing to do with the data has already been existing in the database. Okay, so RisingWave is such a streaming database. It's open source, so it's under Apache 2.0 license. You are free to use in any way you want, and it's distributed, meaning that it is scalable from day one, right? And it's also SQL-based because SQL is still like the dominant language in data engineering. And the primary goal of RisingWave is to focus on two things. One is cost efficiency. I think for this part, like everybody is fully aware of that, right? But a more important goal is really trying to improve the usability. The reason is because streaming processing in general, I would say it's not as mature as OLAP, right? And because some of the existing system, people have the impression that you have to learn a very special type of language to use stream processing. You have to learn a lot of stream-related concepts. But in RisingWave, actually, you don't need that. You have very low learning curve. If you can use Doris, I'm pretty sure you can get on board RisingWave within like 1 day. So more specifically, RisingWave, on the aspect of easy of use, RisingWave is compatible with PostgreSQL syntax. Right? So of course, we support some streaming-related syntax, but it's purely optional. You can just use your knowledge of Postgres to run queries in RisingWave. And the key feature is like create materialized view. By that, we will define a streaming job that is incrementally computed. And we also have both the streaming processing and the batch engine in RisingWave, which means that after you have this materialized view in RisingWave, you can do the serving part, right? We encourage the user to deploy Slack queries in RisingWave to fetch the result they want. For the second part, cloud native, it's a buzzword, but more specifically, we have this storage compute decoupling architecture. I think this is like the norm of all of the modern databases, right? And more specifically, we are optimized for the large state maintenance. So in Boyan's talk, he mentioned that they have really large state when doing multi-stream joins, and that state can be kept for like days and even months. Right? So a lot of existing streaming system fails to perform very efficient join when the state gets very large. And the third thing is that we use object storage like S3, GCS, Azure Blob on the public cloud vendors as the default storage backend. So basically, it means that our backend is infinitely scalable, right? So with this kind of a design, we have this benefit of near zero downtime scaling, meaning that if you want to scale in, scale out RisingWave, it can complete under like 10 seconds. Right? It also applies to the fault tolerance. It's just finished within single-digit seconds. And finally, RisingWave not only syntax compatible with Postgres, the catalog is also trying to be as much compatible as possible, which means that any existing tools, like BI tools, maybe federated query engines and DBT, they are all compatible with RisingWave, right? So RisingWave can fit into users' existing tech stack very easily. So here are some of the paying customers in RisingWave's portfolio. Right? We got some big names like Tencent, Pepsi, and you got some quantitative trading firms like this sovereign wealth fund, like Abu Dhabi Investment Authority. We got MetaBit Trading, we got Robinhood. We also have this Web3 company called Kaito, which does data aggregation of off-chain information. Right? So apart from these typical users that we expect them to be focusing on low latency processing, we also have some other manufacturing business, right? Like CBT is a company in mainland which manufactures electronics. Right? So we also have this Northvolt, which is the largest lithium battery factory in North Europe. Right? So this is kind of a surprising, at least to my surprise, like manufacturing business nowadays are also very competitive. So they really want to monitor, for example, their warehouse, like the real warehouse and the pipeline in their factory to maintain competitive cost structure. Right? So at this moment, there are over 250 open source cluster, long-running cluster actually, running across the globe. And we believe that this number is actually underestimated because for a lot of cluster deployed in private cluster, they don't have access to open internet, right? So these telemetries we cannot collect. So real-time data enrichment, which is main topic of this talk. So this is the process of we joining data from multiple sources together, right, to produce a wide table that has dozens of columns, hundreds of columns. The reason we do so is because once we have this wide table, it becomes very easy and fast to query against, right? Because all of the information associated with a certain object, an identifier, or let's say a primary key is all stored inside one row, right? So you no longer need to do any kind of a correlation, and then it becomes super fast because all you need to do is some simple stack queries or simple aggregations. So this is the reason why we do data enrichment, and the reason why we do real-time data enrichment is because, of course, part of the reason is because part of the business requirement, right? As I mentioned in the last slide, even manufacturing business are trying to monitor their factory status closely and continuously. And then part of the reason is also because data enrichment typically happens at the early stage of the entire data pipeline, right? So if you do real-time data enrichment, so you have the option to do real-time or offline data analysis at the downstream. But if you do like batch processing for data enrichment, then all of the following processing has to be batch processing. So after the data enrichment, we ingest this wide table into OLAP system. Here, for example, let's say Doris, right? The reason we do so is because Doris have the column store, right? Enabling very efficient compression to reduce the size of the denormalized tables. They also speed up the queries. But for the joining operation, I think we prefer doing that in a row-oriented storage, right? Because in join, you have join key. You want to match the rows from the other upstream with a certain key value, right? So what you basically do to the storage system is to do point lookup, and this is not a very good, a very efficient operation on column storage. Right? So the common solution in industry for streaming system is rely on embedded storage like RocksDB, right? LS-based tree engine, and some other solution they also rely on external system, but this is relatively, let's say, a rare case. So here we have like a good combination. Use row-based streaming database to do join, and then we use a column storage OLAP system to do ad hoc queries. So there are like a few challenges when we're doing so. The first one is like various data sources, right? So we have databases as an upstream, we have message queues, we have file systems, and more importantly, when the schema, for example, of the data sources change, what should this streaming database do to react to these changes? Right? The second thing, again, the large scale maintenance. When you do multi-streaming join, you basically need to materialize the data from all of the upstreams. Right? That's the reason why you can do incremental computation. And not just data from upstream. When you, for example, do the drawing of two upstream, you will produce an output stream, right? So when the output stream is again joined with another upstream, its data will also need to be materialized, right? So basically, when you have, let's say, n upstreams, the size of the number of the streams that you really need to materialize is not linear; it's actually n squared. So, and finally, there are also some challenges when you try to stream the changes into data warehouse. For example, let's say the downstreams fails. What should the streaming processing system do to make sure that the system is still available? Yeah. So, sources we have like CDC events from databases. These databases are typically TP databases. In RisingWave, we support MySQL, Postgres, SQL Server, and also like TiDB with MySQL compatible. We can also support them effortlessly. And we also have messages from our message queues and the file system. These are basically append-only events like tracing and logs, right? And we also have various format support, JSON, Avro, CSV, and I forgot one, which we also support like raw bytes. Right? Sometimes the user have their data encrypted, so they have to ingest raw bytes first, and then decode the data, and then process them. And right now, for example, in Kafka, we also support a schema registry. Right? Kafka itself does not really have a schema, so you rely on the registry to fetch the schema. So speaking of schema, we also do like an auto schema mapping and evolution, which means that, for example, when you create a source from an upstream database, you don't need to list all of the fields, all of the columns, names, and the types in the upstream database to be ingested into RisingWave. Right? And when the upstream database schema is changed, like add a column, drop a column, or change the data type of a column, RisingWave can sense that and make according changes in RisingWave. And one difference between RisingWave as a streaming database versus existing stream processing system is that RisingWave can materialize data in its own storage engine. Right? So for example, if you're familiar with KSQLDB, Kafka Stream, Flink, what they do is that they read some data from external system, process them, and then just sync the result to the downstream. Right? The data never materialized in the system. But in RisingWave, you can use this create table statement, right? So you can materialize the data, so we can support like primary key constraint, right? Because you have the data stored, then we can do the check. And we can also do all kinds of DML statements like insert, update, delete, to make the table in RisingWave as the source of truth. Right? Otherwise, you have to rely on the changes made to the upstream database to reflect the changes in your materialized view. Okay, so the second challenge is large state maintenance. As I explained before, if you have multi-way stream join, inevitably you will have a very large state, right? So in existing system, people use like watermark, TTL, weighted join to bypass such challenges. But the problem is that they all kind of limit, let's say, the state size, the duration of the state you want to keep, and the consequence is that they may produce incorrect data, right? Inconsistent data. Sometimes it is okay if your business requirement allows that, but most of the time, I would say people would still prefer like using consistent data, right? Especially they can now learning these extremely specific concepts and just do the normal joins they used to do in OLAP database or in OLTP database. Right? So inner join, outer join is still like the most popular option for data enrichment, and then inevitably you will have a very large state. So the way we do that is that we have first have this tiered storage system, right? All of our data is made durable on S3. And the local disk and memory is only acting as a cache, which means the compute node is stateless. So whenever the compute node crashes, or let's say you need to scale in, scale out, you can just route up a new compute node and it can continue processing by fetching data from S3 immediately. And the other benefit is that your CPU cost is no longer coupled with memory or disk cost, right? You just buy whatever resources that's your current bottleneck. We no longer need to do like watermark, TTL, waiting to join, because the state is basically unlimited on S3. It's infinitely scalable. So with this kind of design, we can tolerate like TB level of state in a single RisingWave cluster. And finally, one feature we have is called a serverless compaction. So remember we say that we have a storage engine. This storage engine is a LSM tree-based storage engine, meaning that from time to time it has to do some compaction to maintain the read performance. Right? So normally the compaction is done inside the same process as the computer is running, right? And the problem is that normal computation and also compaction, they both consumes a lot of CPU resources, meaning they have CPU contention, CPU interference. So the streaming job will get stuck, and And even worse, sometimes if we, let's say, have some data skewness, in some compute node, the data is kind of totally stuck while we have a lot of idle resources on the rest of the nodes. So by decoupling compaction from the computation, right, we can just scaling in and out compaction individually, right, independently. More importantly, the compaction workload is kind of you have high and lows, right? It's periodic, so it's perfect for serverless processing. Basically, you can just schedule a temporary pod and do the compaction. Once the compaction workload reduced, then you just cancel the pod and continue the normal processing. Okay. So the final challenge is to do the streaming ingestion to the warehouse. One thing that I forgot to put onto the slides is that in Doris we have this streaming load API, right? So, but if you go back, let's say 3 to 4 years, most of the OLAP systems do not have this streaming ingestion support. They require you to accumulate the data like per hour, and by the end of that hour, you ingest it into the OLAP system. And now we have the streaming load, we can really make this real-time data enrichment possible. Right? And the second feature Doris has is partial update. Right? If you think about it, when you have dozens of columns in the Y table and you make some change in the dimension table in upstream, very often the only thing changed is like the values from single or two columns. Right? We don't really want to sync the entire chain, the entire row, consistently of like 100 columns to the downstream. It's a waste resource. It reduces the write throughput. Right. So the final feature is in RisingWave is called sync decoupling, meaning that if, let's say, downstream system is unavailable for some time, right, RisingWave can continue processing, and the result will be buffered in S3 in RisingWave's own storage engine. Right. So basically, the sync failure is not decoupled with the processing. So you can continue computations even when there are errors in the downstream. So when the downstream recovered, then the RisingWave will just fetch the output from S3 and continue ingesting into OLAP system. Yeah. So one powerful feature in RisingWave is called materialized view, and even more powerful, we can build another layers of materialized view on one materialized view. Right. So the reason it is very important is because it can kind of reduce the repetitive computation, right? You can do computation sharing. Meaning that, for example, here we have a sales and order example. I will first do some join, and we have this basic enriched orders table, right? This long table here. And then, according to the requirements from different business units, the base table, the base materialized view, will be joined with some other sources to have a more fine-grained wide tables. Right? If you don't have a materialized view built in your streaming database, you have to sync the outputs to some message queue like Kafka, right? And then you read it back. That will put a lot of pressure on the Kafka, and more importantly, Kafka stores all the deltas and updates, which means that even if a value is not changed after 10 updates, you still need to reprocess these 10 updates, which leads to very unnecessary computation. But in RisingWave, you have a materialized view, which means it's a snapshot of all the updates applied, from the beginning until now, right? So the amount of data you really need to build another materialized view is greatly reduced. So in this picture, this is the idea I just mentioned about is more obvious, right? So without RisingWave, you have to go through Kafka. You actually have to go through Kafka multiple times. This is what we normally see in users' production cluster. And with RisingWave, all of the transformation can all be done in RisingWave. And eventually, you sync the data into an OLAP database, into a message queue, or you can allow users to query the materialized view in RisingWave direct. Right? Meaning, you probably, if let's say the size of the data is not too large, you can also save an OLAP system in the downstream. Yeah. So in terms of the Postgres compatibility, not only we use the syntax, we use the concept of materialized view, we also try to be compatible with Postgres catalogs and a lot of catalog functions. Right? So we can connect to superset or finite metabase Cube.js without much effort. Right? And we can also let Trino, PostDB to read the data in RisingWave by constructing an external table. Right? So more importantly, I think Postgres is really a mature database. And if you look at the current market, there are also a lot of popular SaaS products building on top of Postgres, like Neon, like Supabase, right? So which means that we have like a really large, let's say, material for the AI to learn nowadays, right? So you can just ask the AI to write SQLs for RisingWave, and you don't need to write a single line of SQL anymore. So there are some use cases in RisingWave, for example, rules engines. Right? So some financial data platforms like allows their users to do like alerting and monitoring. For example, for crypto companies, they can allow users to configure a real-time alert saying that if the Bitcoin price goes up and hit, let's say, 70K, right? So it sends the output to the downstream so it can notify the user via, for example, WhatsApp, Telegram, or whatever. Right? So a lot of companies, they embed this alert logic into the UDF. Right? So RisingWave supports like two kinds of UDF. One is embedded UDF, meaning that you can just write UDF just as a normal SQL query. Right? So in pSQL, once, for example, you write a UDF like create function, and then you write a Python code or JavaScript code or even Rust code, and then you say end function, right? And then compiles, and then immediately you can use this UDF in the following select queries. And we also have this external UDF, like we allows users to host an external UDF server, meaning that you can kind of avoid like CPU interference between RisingWave and the servers. And more importantly, in the embedded UDF, we disallow users to do network function calling because network is always kind of a security risk, right? But in the external UDF server, users are free to do anything they want. If you favor like ease of use, you can write Python code as UDF. But if you more focus on the speed and efficiency, you can use Rust, and it will be compiled into WebAssembly for RisingWave to execute. The other database is called the real-time data marketplace. We usually say like data mart, or sometimes people also use microservices in this architecture, meaning that you have a lot of teams, for example, in one organization, right? And the people expose the materialized view as like a public interface for other teams to access, right? We also, has this permission and mission control system, right? So we can grant different permissions to different users, different teams, so that one user on one team can only see the data we want to expose. Right? This is a very powerful paradigm, in especially the large enterprise where you have multiple teams. Yeah, so CBT and Kaito are like two early adopters of RisingWave, right? So CBT, they have like 20 rejoins in their cluster, and they are using reasonable resources, like 64 CPU cores and 256 gigabytes of memory, right? So they're doing 20 rejoins, and they have 11 materialized view in the 38 tables. And for this like single state, they can reach like 185 gigabytes, right? If you combine all of these states together, it can reach like 1 TB. And for Kaito, this is the the Blue Engine case that I'm referring to. Right? They have like a little bit less than 1,400 materialized view in their cluster. They have 8 compute nodes, each with 64 CPU. Right? And more importantly, RisingWave supports so-called dedicated serving node, meaning that the streaming processing will happen on a set of compute nodes, and the batch querying will happen on an independent set of nodes. So the SLA of stream processing and the batch processing does not affect each other. Yeah, so basically that's the end of my talk. We have GitHubs, we have documentation, we have a lot of webinar and webcast on YouTube, right? And in the GitHub, we also have the link to the Slack channel. We have like 2,000 members in our open source Slack channel. And if you want to use RisingWave, just one line of code, you can get started in using PSQL to connect to RisingWave and play with it. Okay, yeah, that's all. Thank you.